Hi everyone. Today I'll be talking about privacy leaks from code generation language models. This work is in collaboration with my colleagues from New York University, Liang, Zayd, Maradni, and Christina, Pöpper. Recent improvements in language models have led to larger models, which can be scaled for billions of parameters and can be trained on large scapes of data. This progress has introduced new tools for code generation and code completion, with some of these tools already amassing more than 1 million users. Back in 2021, GitHub released Copilot, which was then followed up by Amazon and Replit releasing Code Whisperer and Ghostwriter the following year. Very recently, Google and Hugging Face also released their code generation language models called Cody and StarCoder. Looking more into GitHub Copilot, it uses OpenAI Codex model, which is a descendant of GPT-3 language model, and trained on 54 million public GitHub repositories. It generally works for two types of input prompts. The first one being the commands, which are directions to the Codex model given in natural language to produce code. The other one is the code snippets itself, which are incomplete snippets awaiting Codex's completion. It is well known that GitHub repositories are known to contain sensitive personal information. In addition to that, these models may also be trained on private user data as well. This, along with the rising use of code generation language models, requires us to systematically assess the privacy implications of these tools. In this work, we introduced a systematic and semi-automated approach to uncover privacy leaks within these code generation models. Our pipeline begins by identifying the potential categories of privacy leaks. From there, we craft input prompts and fine-tune parameters tailored for the Codex model. Once we have fine-tuned the models, we query the model and receive the outputs from the model, which includes both the response tokens as well as the log probabilities. We employ a semi-automated evaluation to detect any privacy leaks, starting with membership inference and later on with verification using GitHub Search API as well as manual verification in the process. This process results in identification of leaks. Starting off with the categories of personal information, we categorize the information that usually appears as targets of privacy attacks and could be part of the code repositories used for the training of the language model. These range from personally identifiable information to private information to secret information. We then start designing our prompts, starting off by looking at handcrafted prompts that are promising in inducing privacy leakage from these models. We then leverage template-based prompt construction to exponentially expand our prompt repository, as well as add diversity to our prompts. Lastly, we complement our prompts by sampling some data from the GitHub repositories for which are more likely to have been used for the training of these models. Zooming in on the template-based prompts, in order to increase the diversity of our prompts, we take into account two meta variables that are provided by Codex API. These are prompt style and programming language. Prompt style, again, refers to, as I talked about earlier on, about the type of prompt, whether it's a command or a code snippet. And programming language is about whether it's Python, SQL, or JSON. For contextual variables, these are additional variables that we have noticed to add diversity to our prompts as well as the outputs that we receive from the model. And these are context, prefix, and natural language. Context here refers to whether the prompt that we use to query the model provides any specific context or is it generic. The prefix, as the name explains, includes a prefix of the data that we are querying for. And lastly, we query using both English and Chinese languages, the two widely spoken languages. Temperature tuning in language models is an approach to balance output diversity against determinism. As we can observe, lower temperatures distinctly skew the distribution in favor of higher probability values. And our findings indicate that for general prompts, a higher temperature is optimal to encourage diverse outputs. However, For specific prompts, they benefit from a lower temperature, ensuring deterministic outputs aligned with the given context that we have provided to the model. By now, we have looked at the steps needed to query the model. We query the model and receive the outputs. And now the rest of the presentation will be looking into analyzing those code generations for identifying privacy leakage. Given the constraints of our attacker model, which operates under the black box assumption, and considering the impracticality and costs associated with training shadow models for a large-scale model such as Codex or GPT-3, we have adopted the blind membership inference approach. The main premise here is that members and non-members belong to different distributions. Removing a non-member from a mixed data set pushes it closer to the member distribution. So basically, we systematically move samples from targets to non-members, measuring the distance between the two sets each time. If we notice that the distance increases, the sample finds a new home in the non-member set. Otherwise, we revert the change. This iterative process continues until no further move leads to a larger distance, meaning the two distributions are as far as possible, and the members are separated from the non-members. We cannot blindly apply the blind MI attack to the case of language models, precisely because language models output a probability vector of sample tokens with vocabulary that can be as large as 50,000 tokens for the case of GPT-3. Specifically for a Codex model, it only provides access to the top 5 tokens alongside probabilities, which is a tiny fraction of its entire vocabulary. And the potential leaks that we are interested in are sequences of tokens, not individual tokens. Thus, we evaluate the role of subsequences length, feature selection, and in the initial split size on the approach's performance. As far as the subsequence length is concerned, we recognize that to be able to capture and memorize subsequences, we try to zone in onto the subsequences with the smallest perplexity within the whole output from the model. As far as the features are concerned, we move away from the naive log probabilities and incorporate a variety of perplexity-based features. And for the initial split size, we understand that the privacy leaks in language models do not necessarily have the lowest perplexity. An output that is completely generated but is correct and natural code will have lower perplexity than a randomized password that is part of the training set. So we perform a systematic search for an optimal initial split for the blind MI attack. We evaluate our approach on a variety of code generation models ranging from star coder, polycoder, and CodeParrot, and we optimize for higher recall for members and lower ratio of members that are left in the dataset after the removal of non-members. As we can see across all these models, we are able to filter out roughly 20 to 30% of non-members from the dataset while still retaining a reasonable amount of recall for members. Having applied this blind membership inference attack on our Codex model, we then subsequently perform verification checks on through GitHub Search API, as well as manual evaluation, which results in the discovery of 43 leaks, which is essentially around 8% of the input prompts that we utilized. Roughly 1/3 of these leaks are targeted leaks, which means that there was a direct correlation between the prompt subject and the model's response. For the rest 2/3, those were categorized as indirect leaks, which meant that there was a valid information that was leaked from those models, but that did not belong to the individual that we were querying for. That said, it still compromises the privacy norms as contextual integrity for the other individuals involved. Here I provide masked versions of some of the leaks that we've identified. We also assessed the attack against a simple baseline of searching the input prompts on the GitHub search. And we identified that our approach was able to identify leaks at least 5 times higher than the baseline. So in terms of takeaways, we propose and develop a semi-automated pipeline to test a code generation model for privacy leakage. We would assume that this kind of method could be utilized more rigorously to audit language models for privacy leakage before they are being sent for production. We reveal that identifiable information like addresses, email addresses, phone numbers, and birth dates face a higher likelihood of leakage. Codex model tends to release related information about other individuals in the same code file that we are querying for, which poses privacy threats as contextual agreement. Cleaning public repositories of these personally identifiable information isn't going to be the complete solution, primarily because these models are also trained on private user data as well. And lastly, we need advanced protections for reduction of PII from code generation models that go beyond the verbatim blocking filters. With that, I would like to thank the team that worked tirelessly on this project, and I'm happy to take any questions that you have.